Right. So the emulsification. So what do you mean by the emulsification? Anyone can answer? What is the emulsification? What is the emulsification?
Breaking down of lipid substances into small droplets of lipid.
So incorrect answer, breaking down the lipid droplets to the smaller portions. No, it's not a emulsification. Any other answer? But thank you for answering. Though it is incorrect, I will explain you why it is incorrect. Another answer?
Excuse me, madam. Madam, emulsification is a process.
Madam?
Yeah, the one person is sleep. Yeah. Anyone, you can speak very loudly, then other ones know that you are speaking. The answer?
A system of holding two immiscible phases together.
Yeah. Yes. Emulsification, basically we want to immiscible two, if there are any two immiscible phases, we want to mix, generally they are unmixed, but by using the emulsification we want to make it mix, right? So in such situation, actually the breaking down the lipid particles to the smaller particles mean that is actually the particles are the same. That means if the lipids are, the lipid globules are bigger one, and if they are a smaller one, but those are lipids. But here we are the lipid break down to the smaller sizes. So we can do it by just get the lipids, and then if we are the mechanical, if we give the shearing force, then bigger droplets we can break down to the smaller droplets, but those are still in the bigger droplets. But when you are using the shear force to break down that to the smaller droplets, sometimes because of the shear force, that the air can be incorporated to the system. Therefore we can't say actually it is emulsified, because we can say sometimes it's emulsification, but actually it's not, because there is only the air and no air and lipids. Those are two different systems, but it's okay. But making it to the small droplets, we can't say it is a kind of thing, because it's a kind of a breakdown in the particle size. The bigger one to break down to the smaller one, there is a breaking down the particle size, that is only. So breaking down the particle size of the smaller one is not the emulsification. In case of the emulsification, always there should be two immiscible liquids or two immiscible phases. Sometimes it's water and lipids, and sometimes that the water and air, or sometimes lipid and air, kind of two immiscible phases should be there to make a emulsification, right? So the emulsification, always we talk that we consider that there is a two immiscible phases. Therefore, it is difficult to that two immiscible phases cannot be get together. Those two phases always like to come to the maximum equilibrium situation, and if according to the densities, they will go up or down. So in the case of water and lipids, that the lipid is always the less density, therefore it is come to the top of the lower water layer, and the water is going down. But in the case of food processing, or when we prepare the different type of food, we need to come out with the good solution. So that is why we make the emulsification, because in some, let's say now, if we want to eat salad, we want to add some kind of some dressing. to prepare the dressing, we can't, in the case of sometimes there's a dressing, some people use the totally olive oil, that is only olive oil. But having such a large quantities of oil is not good. Therefore, and the taste is very bland, only olive taste. Therefore, and the oil taste. Therefore, we can add some water, and when we add the water to that dressing, with the water soluble some other other ingredients or the other flavors or the aromas or the some different things, ingredients we can put it. And finally, that dressing is going to be a very eatable, palatable, and you like it, and so many sensory attributes we can put to the emulsion, because we are going to we are going to that dressing, because it's a really nice one. To do that, actually, if the two phases are there, oil is on the top layer and what is in the down layer, we can't do this. That is why we want to introduce the emulsion. So in order to form and stabilize an emulsion, we have to add the protein, because we want to mix that two layers together. Therefore, we add that these emulsifiers. Why we because the importance of adding the protein to the stabilized emulsion is because protein has the plus and minus charges. You know that because amino acids basically having the plus and minus charges, accordingly proteins also having the plus and minus charges. And also the plus and minus charges, as well as there is a polar head then non-polar tail. The non-polar tail like to mix with the lipids, and the polar head would like to meet with the water. According to they come to the diffuse phase, mean that water is the lipid is there in the top layer and the water is there at the bottom layer. The adjoining phases we call the interphase. Therefore, protein can go to that interface and stay there, and then it is protein unfolding happening and expose hydrophobic when the protein is happening unfolding, you know that the hydrophobic phases or the groups can be exposed. Therefore, those hydrophobic one go to the lipid part or this join with the lipid part, and the hydrophilic one go to the and join with the water part, and therefore then it make a kind of a interaction with the lipid and the water. In the middle, the proteins are there. Therefore, the interaction of the lipid can be happen with the protein, as well as interaction can be happen with the protein with the water, right? Therefore, in order to form and stabilize an emulsion, as a protein must have these qualities. It should go to the diffuse to the interface. It can be unfolded. It should be unfolded. Hydrophobic groups should be exposed, and also it should be interact with the lipids. So if there are these four qualities in the protein can make work as a emulsifier. So when we talk about the protein diffusion and emulsions, protein must diffuse to the interface. Rate of diffusion affected by the presence of salt. So if you are tasting different type of dressings, salad dressing basically, so you know that there is a salt taste is there. So without salt taste, the dressings are not there. Actually, almost all dressings are having the salt taste, because rate of diffusion is affected by salt. Therefore, if you are adding the salt, you can increase the diffusion rate. Rate of diffusion affected by also the viscosity, and therefore most of the salad dressing if you go to the wedding, you can see different type of salad dressings are there, and those are affected by the viscosity, and most of the salad dressings are having a thick, those are the high viscosity. Therefore, it is very important to make a good emulsion. Most studies indicate that diffusion from the bulk phase to the interface is rate limiting. Therefore, that means diffusion from bulk phase to the interface rate is limiting. However, so it is supporting to make it as it's together. So finally, you will end up with the kind of one liquid or the one thing, but it is not two separate immiscible phases. You can't see if you added the emulsifiers to the product. Then emulsification and temperature also having a very good relationship. Emulsion formation favored around 60 degrees and the lower viscosity, and but in the high viscosity it is getting a high viscosity and low temperature. Actually it is low means not the very low temperature, it's giving a very good interaction. That means you can get this very stable emulsion. It favors hydrophobic interaction, and lower temperature decreases energy barrier to lipid water interaction, and freezing can cause physical damage to the interface. Therefore, normally in the emulsifiers we do not put in the freezers, but in the case of ice cream also the emulsion, but we put it to the freezing because we are adding different other components to not to freeze, though we put in the freezing temperature, but it is not because we can scoop it, therefore we can't say it's totally frozen like ice, right? So if it is ice, then definitely it's a damage to the situation, because what is there, if the ice crystals are formed in the ice cream, then definitely it is really damage to the product quality or product sensory attributes. So now let's learn much detail about how protein is supporting for the emulsification process, because protein can be act as emulsifier. Therefore, it's a functional properties we call the emulsification. It can be work for a emulsification process. As mentioned earlier, emulsion is a suspension of small globules of one liquid in a second liquid with which the first will not mix. Actually, the emulsion is the one liquid is there, the second liquid is there. Those two things are not mixing together. So the first one, or the major one, is dispersed in the major one is there, and the second one is dispersed in the other one. So that is we call the emulsion. The protein can be excellent emulsifier because they contain both hydrophobic and hydrophilic groups. So as I mentioned you earlier, that why protein can act as a emulsifier, because it is has the hydrophobic and hydrophilic groups. So why it is having the hydrophobic and hydrophilic groups? That means because it has a different amino acids, because protein is a combination, or the primary proteins is having you have observed that how that the hydrophobic groups are coming out, right? Then therefore the hydrophobic amino acids are there, hydrophilic amino acids are there, all are in line in together, maybe hydrophobic, maybe hydrophilic. Therefore, as both the protein is having both type of amino acid, that is the one reason for protein can act as an emulsifier. So when you can see the picture, you can see that the hydrophilic head in the hydrophobic tail is there in a protein, and it's a hydrophilic area is having the net charge on the negative charge is there on the hydrophilic group. Sorry, here, right. So if there is a negative charge in the hydrophilic area, then definitely if the water is there, if the liquid is a water or the one phase is water, because H2O having the plus and minus charges. Therefore, the protein can very easily join with the plus charges or with the hydrogen bond, and therefore it is we can say it's a soluble in the water. Protein is a protein what in. It is a solubility is there. We learned it in the previous lecture. And then the oil droplets are there, water is there. So what is happening? Then because of the oil, if it is in the water, the continuous phase is a water. So you know about the continuous phase and dispersed phase. Continuous phase is a bigger one. Dispersed phase is a smaller one. In the case of water and oil, if you are get the water and put some oil to there, if you are shake it very in a high rate or the high speed, if you are shake it, you can see that the oil droplets goes inside the water, and you can see small golden bubbles are there in the water, that is the actually it's a kind of a emulsion, right? But that emulsion is not very it's not stable. Therefore, the always oil droplet is because of the buoyant forces, it want to go to the top because the density is lower in oil compared to the water. Compare the buoyant forces and the gravitational forces. So the buoyant forces is higher for the oil droplet, therefore it is going up. And if the emulsifying agents are there, that emulsifying agent can combine with the oil droplet, as well as it is okay with the proteins. So that is why you can see in this picture, emulsifying agent is there in the surface of the oil droplet. So in this picture also showing that the temporary emulsion or normals, what will happen, that the oil and water in the two phases, the agitation, you can see that the oil droplets are going as a droplet because in the surface tension, always oil is like to be a droplet, right? Get a round shape because of the surface tension. And therefore, so you can see the small globules or the small oil droplets are inside the water. Or sometimes in the other case, water can be again because of the surface tension. If you are putting the much small amount of water to the oil, then you can see the oil droplets there in the water droplets are there in the oil major phase. So in the case of stable emulsion, if you are using the protein as emulsifier, it's a protein can go to the interface, and therefore it can, as I mentioned in the earlier picture, you can see that the proteins are covering the oil droplets. So therefore finally protein and water can keep as it is, because protein support to bond with the oil and water. Protein of an emulsified oil droplet, therefore the hydrophobic regions of protein oriented towards oil phase, and the hydrophilic or the polar regions of protein oriented towards water phase. Therefore you can see that then it's trapped to each other. The dispersed system is very very stable, and they are because of protein. Therefore you can see very unique or the very one liquid there because of the protein. To form a good emulsion, the protein has to be able to rapidly absorb to the oil water interface. So I mentioned four what's the reasons, or four abilities should have the protein should have. And in this case also, the rapidly absorb to the oil water interface is the other ability protein should have to be a emulsifier. It should be rapidly absorbed to the oil water interface. That means it's quickly it should combine with the oil and the water. Rapidity and readily open up and orient its hydrophobic groups towards the oil phase and its hydrophilic groups to the water phase. And form a stable film around the oil droplet is also needed to make it you have seen that the earlier picture that here how it's in the surface, it's preparing a small film. So that film should be prepared. If not so, it is not quickly work out to be to make a emulsion with nice emulsion. So when you see this picture also, you can see that the non-attractive interaction between droplets, you can see that attractive interaction between proteins are there in the left side top corner, that figure. You can see the green color one is non-adsorbed protein, and the yellow color one is oil droplets, and the other one is emulsifier. So there are some non-absorbed, because they are the protein means not all the proteins are not working, but there are some non-absorbed protein also there. It is there in the surrounding, but the quickly working the proteins can be there in the surrounding the oil droplet. In the other case, the non-attractive how those are working. The left side top corner, you can see how that if there's a non-adsorbed protein as well as the emulsifier proteins and the oil droplets are there, how those are working, right? The other one is non-attractive interaction between protein. Also, you can see that the green color non-adsorbed proteins are there, but it's again surrounding that the emulsifiers are there, and it's working with the very nicely with the oil droplets. And the other one is you can see that the left hand side bottom one, attractive interaction between droplets, attractive interaction between proteins. Also you can see how these are getting together. Now here you can see, compare the left hand side, the top one. Here then all other proteins are getting surrounding, and the oil droplets and the emulsifiers are getting together. And other one is non-attractive interaction between proteins as well as the attractive interaction between proteins. Those are in the other one, the right hand side bottom one, you can see different one. But when you compare these four pictures, you can see four type of systems are there. But here we are not talking about the oil or the water. Oil is there, but we are not talking about the proteins. But sorry, not talking about the water, but here the protein and oil and emulsifier, how those are working, showing in this picture. Protein, lipids and emulsifiers, how those are working. In the case of now you can see that at the beginning it's a different one. Oils are get together, dispersing the protein in the let's say the first picture is A, and that means left hand side top one A, right hand side top one B, and left hand down bottom one is C, and right hand side bottom one is D. If we consider like that, you can see, but the four situations are different. But even those situations that we can see, all those situations we can consider as emulsions. But in this case, the protein is there, lipids are there, emulsifiers are there. But all the situations are emulsion. Right? Now this picture you can see protein surfactant interaction. Surfactants are there. Then how proteins and surfactants are working. Formation of protein surfactant complex at oil-water interface, you can see in this picture. The blue color one is non-micelle caseins are there, and the yellow one is the oil droplets. And there you can see even polysaccharides also in the down picture. But before we come to that point, let's see the top picture. Smaller molecules with surfactants also there, and how those are making an interface. Surface protein displacement by surfactant, and earlier surfactants are there, but small molecular weight in the surfactants are there earlier, and later on that the proteins also there. The later on how that the protein is this protein is sent away by the surfactant, and surfactant try to make a emulsion. The second B picture, protein-protein interaction, you can see how these things happen. Then there is a pink color one is the denatured whey protein, and the blue one is the non-micelle casein. So both are the protein types, but the first one, the denatured whey protein, is attached to the droplet. And if you added the different one, then here that the casein incorporation of that oil and water interaction, all are get together and make a very good stable situation, the protein-protein interaction. In the other case, the casein and water is there in the second layer, that the casein lactoferrin is there, that how these are when it come to the third layer, the water, oil, and what is the blue lactoferrin as well as the non-micelle casein, all are together, then produce a very stable emulsion, oil in water emulsion. In the C picture also showing the protein polysaccharide interaction. Therefore, in the similar case, that is again that earlier caseins and water is there, oil is there, and oil water casein are there, first picture, C picture. And the second layer, once you add the polysaccharides, then the casein polysaccharide interaction is there, and finally you can see all get together and finally giving a very stable emulsion. So therefore now you can observe that the protein can work as emulsifier, as well as the surfactant also can work as emulsifier, as well as the polysaccharide can work as emulsifier. Those are the three different emulsifiers normally we are using. But actually the protein is having an ability to work together with any kind of the other emulsifiers. That is very important characteristic of the protein. So therefore, if you add the small protein, the casein, whey protein, or the casein, or the another protein, you can work, or the soy protein, whatever the thing. So those are working a very good emulsifier, and finally you can go for a good productive. Finally, you can come out with the very good product. So the concept now you have up to now you have learned about some important features of the protein. If protein is want to work as an emulsifier. Now let's see some other things. The one is distribution of hydrophobic versus hydrophilic amino acid is really important of the important feature of the protein. It's the proper balance is needed, because if there is a hydrophobic one, things are the high, then it is not work properly. Therefore, the very good, if the very good balance is there, the hydrophobic and hydrophilic amino acids together in that protein, it's work as a very good emulsifier. Because you know that the proteins are there a lot, right? Plant protein and the milk protein, as well as the meat protein, fish protein, gelatin, a lot of things are there. But in the case of as emulsifiers, we are not using all type of protein, but special proteins we are using as a emulsifier, because those are having the proper balance. Increased surface hydrophobicity will increase emulsifying properties. So if the protein is having a surface hydrophobicity, that increases emulsifying properties. That means when the protein is unfolding, or the unfolding or without unfolding, hydrophobicity situation is very high, then it can be act as a it increase the emulsifying properties, because it's a quickly go to the surface or the interface and start working together, start working the link with the hydrophilic hydrophobic areas, or the water and the lipid can link together. The other one is structure of protein is important. Globular is better than fibrous protein. Now the globular protein, the fibrous protein, when we talk about the meat and the fish, and those are having the fibrous protein. But in the case of plant protein is having the globular protein, because actin, actomycins, those are the fibrous, because in the muscles are having the fibrous protein. And the globular protein is much better, because it's a globular type, and it can move very easily, because it's not a fiber, not a very stick one. Therefore, the globular protein is much better. Flexibility of the protein is the other one. More flexible it is, easier it opens up. So if it is more flexible, it is easier to open up. Right? Then therefore because I mentioned you that the hydrophobic groups should be open very quickly. If it is open hydrophobic group very quickly, then it can join with the hydrophobic group, right? Then other one is the solubility. Insoluble will not form a good emulsion. It can't migrate well. Please. Isoelectric point is not good. So insoluble will not form a good emulsion. Therefore, the solubility of protein also very important. That means the solubility. Then you have to consider the situation. You go through the slides again about the solubility, and then if it is not soluble, then it can't migrate through the water to whatever the required place. Therefore, solubility of the protein also very important. Now in this case, you have to think about that the pH. pH is really important. If the pH is equal to the isoelectric point of the protein, definitely this that means it's make a gel. Therefore, the protein can't move to the interfaces wherever to meet the lipid, then it's not work well. Therefore, the solubility of the protein important. And in this situation, isolatory point is not a good pH level to make an emulsion. Increase in solubility, increase the emulsification ability. It is up to a point. Right? So those are the important protein features should have to make a protein as a good emulsifier. Emulsifiers are characterized by the emulsification capacity and emulsification stability. Now, protein can act as emulsifiers, but emulsification capacity, emulsification stability can be changed according to whatever the protein you are going to use as emulsifier. When we talk about the emulsification capacity, oil titrated into a protein solution was with mixing, and the maximum amount of oil that can be added to the protein solution measured. Emulsification capacity, that means we can do that the oil titrated in the protein solution with mixing, and maximum amount of oil that can be added to the protein solution can be measured at the beginning and before we add it, because we should have to know what is the emulsification capacity of this protein. The other one is emulsification stability, emulsion formed, and it's a breakdown, separation of water and oil phase monitored with time. So once the emulsion formed, without doing anything, we have to keep it as it is to see how long this protein can make this solution as an emulsion, right? So then there's emulsification stability and emulsification capacity of the proteins are really important before we selecting the emulsifiers for respective product, right? So if you have any question, you can ask now, or if not so, I have to answer later on after we go to the after finishing this lecture to the go to the see in the chat box, right? If you have any question, please type it in the chat box. Then shall we move to the forming characteristics? Forming. So when we talk about the forming also the kind of we can say it's also the disperse system, because the form means in the case of emulsion, basically we consider that the water and oil or oil and water, right? The two things is a tangible one. But here when we talk about the forming and lipid, the forming is air. All the time when we talk about the form, it's air is there. Now we are going to learn about how that the air incorporate to the system and how protein are supporting to make air incorporation to the system. Then the forming and the presence of lipids interferes with formation of forms, right? For high fat products must have one type of protein to form the emulsion and another to incorporate air. Now here if the product is in this case even the lipid interfaces with the formation of forms, lipids and air. For high fat products must have one type of protein to form the emulsion and another to incorporate air. That means if the product is having the high fat, and if you want to incorporate air to the high fat, in such situation you need the two different type of proteins. Low fat forms are often made with egg white, while high fat forms are often produced with casein. Now that means if you are going to make a form by using the low fat, then you need a different type of protein, and if you are going to work with the high fat forms, then you need a different type of protein. That in this situation, the egg white is not suitable for high fat emulsifiers to make a form, but in the other case, casein is not suitable for a low fat one, right? The form stability also depend on the form factors that decrease the form stability: gravitation and drainage, capillary pressure drainage, mechanical disturbances, factor that increase form stability, for example, surface viscosity, gives a Maragoni effect, and electric double layers. So those are also depend the form stability, because the forming is we work with the air. The air is having a not like a oil droplet or not like a water droplet. The air is having a different thing, different. It's a different physical status. Therefore, all the time air is it's like to. It much like to go forward, because it's because of the buoyancy effect of the air bubbles. Therefore, these are depend on the surface viscosity and Gibbs-Maragoni effect and electric double layer. But this later on, the Gibbs-Maragoni effect I am not going to discuss under this lecture. And when we talk about the for functional requirement of food protein ingredients, especially when we talk about the properties, the sensory properties, visual, hydration, surfactant, textural, rheological, and other properties, those are give to the, those properties are give to the functional attributes. So I will come to this slide later on at the end. And okay, now again, when we talk about the forms, forms are very similar to emulsion, where air is the hydrophobic phase instead of oil, right? So it is forms are very similar to the emulsion, but air is the hydrophobic phase instead of oil, as I mentioned earlier. And principle of form formation is similar to that of emulsion formation. Most of the same factors are important. Now you can see in the beer glass is there, you can see the forms are there. But here even that this is very, these forms are, you can keep it, you can see it there for a longer period. Therefore, to make it in the, because water is there in the forms or are formed, so what are the things support for making these forms, right? So normally the surfactant solutions, you can see here the gas also there, and the surfactant solution is support to these in you can see the small tail and head is there. So those emulsifiers are supporting to make forms, right? Because always that the gases are there, you can see now the forms are coming out to the air phase. So the normal environment is having air, and the liquid is there, and once that the air bubble is coming out from the water or liquid, and it exposed to the air. Therefore, in the surrounding of the air bubble as well as the interface, the air and liquid interface, as well as the inside the solution, as well as the top layer, also they are having surfactant solutions. Sorry, they are having emulsifiers. Forms are typically formed by injecting gases, air into the solution through small orifices, and mechanically agitate a protein solution. Also whipping, also we can make a air incorporation to the product. Gas releases in food also make emulsion. Therefore, for example, leavened bread's a special case, or especially the bakery products basically. So you can see that the gas release in food because of the leavening agent. Therefore, the forms are typically formed in the three situations. The first one, you can incorporate the gases to inside, and the other one is mechanically agitate to the protein like whipping, or if not so, it is automatically release gases like carbon dioxide during the bakery products producing. Proteins in forms contribute to the uniform distribution of fine air cells in the structure of foods, and body and smoothness of food forms is related to the formation of air bubbles that allow volatilization of the flavors and enhance palatability of the food. Now this form is, why that form is very important, because it's a very important for a, because palatability. And also this air bubbles, if the air bubbles are inside the product, that the flavors or the aromas can trap by the air bubble. Therefore, once you eat or once you smell when you check the aroma of the product, because of that the forming properties, that the air bubble, the entrapped flavor, entrapped aromas can come out, or the flavors can come out from the product. So accordingly, that forming is really important. For example, that now sometimes so the beer in the case, and what are the other example of that the forms are there, because if you are actually the flavors can the flavors can trap by the air, or they can because some flavors is volatile flavors, definitely it is there in the inside the air bubble, right? So you can get some example. What kind of example we can see? Okay, time being we can find out some example. You also think about that. Therefore, the very nicely you will feel that the product is really nice because of this situation. Now you can see there is the raw egg white is there at the beginning, 99% water and almost 10% of protein is there in the raw egg white, right? You have seen that. Then when with a little large air bubbles are mixed into the egg white and the proteins are denatured. The proteins are denatured, but you can see that how the proteins are denatured in this picture. Earlier it's like a smaller, not folded one, but time being if you have whipped that one, so you can see that the unfolded protein, and also that the air bubble are incorporated. What happened in the next step, when forms is complete, denatured proteins are oriented around the smaller air bubbles, and therefore you can see a stable form because of you can get because of the whipping or the giving the shearing force to the egg white. Have you seen this? Because the beating is beating means we are giving the shearing force to the egg white. Because of the beating, it will end up with the nicely formed forms. Sometimes there's a bigger one, sometimes it's a smaller one, and if it is coming as a bigger one, later on it's coming a smaller one. However, finally you can see stable forms there at the end, right? So you can see how that the unfolded proteins are support to trap the air bubble inside this water system, because the 10% proteins are there in the egg white, 90% is water. Now water and air emulsion, or the form is when it comes to the form, air we call form, and how support that the protein albumin to make this form. So the factors that affect form formation and stability, first one is a type of protein. The increased surface hydrophobicity is good. If the surface hydrophobicity is good, then if it is having that the protein is giving a very good emulsifier, or the protein producer very nice forms. Partially denaturing the protein often produce the better forms. If the proteins are denaturing the partially, not fully, even also produce the better forms. The other one is globular is better than the fibrous one, as again because globular proteins can move very fastly, and it's very freely move rather than the fibrous one. Fibrous one is attached to each other and having a very big molecular weight in this fibrous protein rather than the globular proteins. So therefore, the type of proteins is important to do as a form formation and stability. Let's discuss about what are the factors that affect form formation and stability. The form formation and stability is often bad at around isoelectric point. So in the case of emulsion, even that the isoelectric point pH is not a suitable one for emulsification, as well as the form formation stability also isoelectric point is not a suitable pH. At the isoelectric point, what happened? The total charges of protein molecules is close to zero, which leads to their aggregation and coagulation. So the aggregation and coagulation of protein then not support for, because it though at that isoelectric point they like to combine with each other, or they like to aggregate. They like to keep together with each other. That's those proteins. Therefore, they do not feel to move to that the interfaces and make their job. So that is why the isoelectric point is not good. The higher molecular weight complexes impair the formation of viscoelastic protein film at the boundary of the two phases, which is mandatory for stabilization of the form. Now, if the higher molecular weight complexes impair the formation of viscoelastic protein film at the boundary of the two phases, which is mandatory for stabilization of the form. Now, the viscoelastic protein films is really important if there is at the two phases, because to make a stabilization of the form. However, in this situation, the isoelectric point is really not a suitable one, or near isoelectric point is not a suitable one to make a form, make a stable form. Factors that affect form formation and stability, the salt is the other one, because it's a depend on the protein dependent. For example, in the case of egg albumin, soy protein, gluten, increased salt usually improves the forming. Since charges are neutralized, they lost solubility and salting out. In the other one is the whey protein. It's increased salt negatively affect forming. They get more soluble in salting in. I have sent you the salting. I have upload the reading material. I think you have gone through it by now. And the much details are giving about the forming, emulsification in that one. And I have I know that if you have gone through that reading material, you can read that about the what is salting in and salting out in detail. Therefore, read it and then you can get much information about the salting in and salting out, right? So in the case of some proteins, egg albumin, soy protein, glutens are much increase in salt is much better for that one, increasing the improve the forming. But in the case of whey protein situation, salting out, the low increased salt negatively affect for the forming, right? Therefore, this salt is, or the iron concentration is the negative effect, and the positive effect in the two different situations according to the protein types. The other one is the lipids. And when we talk about the lipids in food forms usually inhibit forming by adsorbing to the air-water interface and thinning it, right? The lipids in food forms inhibit forming by adsorbing to the air-water interface and thinning it. That it is inhibit forming, because at the it is it's absorbed at the air-water interface and make it because now lipid also, if the lipid is there, lipid also kind of it's a competitor in this situation. Therefore, it is also they go to the air-water interface and it try to add the protein or it try to combine with the protein. Therefore, it is not support for a air-water interface. Or it is getting not the thicker one, make a thinning one. Therefore, the air can easily go out from the water into water, and therefore the bubbles are removing very fast if the lipids are there. Only 0.03% egg yolk, which has about 33% lipids, completely inhibit the forming of egg white. So if you have, this is, I think you have practiced and practiced when you know that if you are going to make a when you are beat the egg white, you can get the forms. But if you are putting the egg yolk together as a full egg together, and if you beat it, you can't get a form. So what is the reason? Because if the lipids are there, it is totally not support for making a form. Cream is an exception where very high level of fat stabilizes form. And but in the other situation, here if there is a small amount lipid, then it is not support for a formation of the form. But in the case of whipping cream in the milk, but it is supporting because the lipid is higher amount. Therefore, it's supporting for the because in the milk whipping cream, the water is there smaller amount, lipid is there higher amount, as also the proteins are there. But in that case, lipid is higher amount, therefore it stabilizes the form because water is small amount. In that case, the air and lipid is make a form, not the water. Water is not much support for the in that situation. It is different. It's not combining with that the form formation, or they're not supporting for the form formation, no interaction, no interfere with the form formation in the cream. Therefore, it's whatever the form in the whipping cream is very stable. You can see that the whipped cream can form formed by using the whipped cream is very stable when compared to the egg white even. And when there are some stabilizing ingredients we can use, as I shown you in the other picture, if you are putting some kind of the sugars or the carbohydrates, definitely that increase the viscosity, and also it is support it go to the interfere with the interface, and then it's support to make a protein carbohydrate linkage or polysaccharide linkage, and then it is support to make a stable the form. Ingredients that increase viscosity of the liquid phase stabilize the form, especially actually viscosity increasing can be done by the sucrose or the gums or polyols, those carbohydrates or the polysaccharides, and those polysaccharides are very much support to stabilize the form. We add sugar to egg white forms at the later stages of form formation to stabilize. If you are going to, in the case of egg white, and you are going to form the using the egg white, even if you add the sugars at the later stage, later is not the beginning. Beginning you have to let it to make a form, and if you are add some sugars to the later stage, you can make a stable form. And in the case of whipping cream, even but whipping cream or originally it's having some sugars, but we're adding some added sugars, the sweetened one, then you can see the whipping cream is having a very nice forms, can keep for a longer time period. Addition of flour, the protein, starch and fiber to form egg white to produce angel cake, a very stable food form, right? So now you can see that these things are very stable, very especially the starch is really supportive to make a form, keep the form very stable. So in the case of bakery products, especially the cake or the bread or the bun or these kind of thing, you know that the protein make a network there, and very much supporting to because not only the protein also there, as well as the carbohydrates also there, and those the fibers also there, all get together, and then different proteins very supportive to produce a very nice form of the air entrapped products. So when we talk about the energy inputs, the amount of energy, what are the speed of whipping and the time used to form protein is very important. So if we are in the case of even that the whipping or the beating, if we are beating egg white for a longer period, you can see that the stability of the forms is broken down, and you will end up with the kind of a liquid. So too much energy or too long whipping time can produce a poor form. Therefore, it's a very nicely you have to make it. You have experience about that, the egg beating. If you have not done yet, please do it. Get a egg white, and then you beating. You can beat in using a different way. Then you can see how these forms are forming, right? And the bubbles are forming, and observe what is going on. You can do it at home. The form structure breaks down, proteins become too denatured, because if you are what is happened there? Actually, if you are introduced too much energy or too much shearing forces, then it is breakdown or the denatured protein a lot. Therefore, finally that protein is not ability to work as a emulsifier. And in the as mentioned earlier, emulsification capacity and emulsification stability, the kind of thing, the form also having the form capacity and form stability. So the form capacity is determined by volume increasing immediately after whipping, and form stability is defined as the volume of the form that remain after time can be expressed as a percentage of the initial form volume. So the form, whatever the protein, if you are going to use for form forming as a stabilizer, then form capacity as well as the form stability is very important in that protein, right? So the now you can understand that when we talk about these proteins are the supporting solubility, gelation, forming, emulsification, and also the viscosity improvement. A lot of functionalities are there. Now 4 functionalities we were discussed here, as well as the external factors or the environmental factors, pH or the shearing forces, it's a processing. Not that means all 3 types, that the 21 factors we have discussed at the beginning, all 21 factors, almost all, sometimes it's not all, but those are really supporting for the stability of the protein, or the protein functionalities, as well as the protein functionalities are really important to come out with the different type of the food products. Right, now let's see, now we can do the protein modification to improve their functional properties. We can do the protein modification because we can do the starch modification, and likewise, then protein also we can modify. So how we can make a protein modified to improve their functional properties? Some proteins don't exhibit good functional properties and must be modified. The other proteins are excellent in one functional aspect but poor in another, but can be modified to have a broader range of function. Because one is having, for example, now you know the egg white is, egg albumin is playing one role, and the whey protein is playing another role. The gluten protein is play another role, and the soy protein another role, and the pea protein another role. Like meat protein, fish protein, different type of proteins are playing different roles in different situations. So how we can modify the protein to make those things playing a very better role to the respective food system. We can do the chemical modification by reactive amino acids are chemically modified by adding a group to them. For example, lysine, tyrosine, or cysteine increase solubility and gel forming abilities. Therefore, if we are introducing or changing the chemical modification and make increase in the lysine, tyrosine, cysteine, then you can increase its functionalities. Modified protein has to be non-toxic and digestible and retain 50 to 100% of original biological value, often used in very small amount due to the possible toxicity. So the sometimes the modification is not good, but in the case of protein modification, it is not much. It's really good. It's non-toxic, and you can increase the different functional properties like solubility and gel forming abilities. So when we talk about the chemical modification of proteins via lysine residues. So the acetyl, then the modifying group acetyl, succinyl, phosphor group or glyco group or fatty acid groups you can put there. And accordingly that the protein is there and it's added with or combined with the other group. Therefore, the effect on protein surface removal of positive charge on lysine. So by adding the acetyl group, you can see in the other C double bond or the carboxyl group, and the next one you have added the acetyl group. Therefore, the removal of positive charge on lysine. Accordingly, you can change. You can you can support it to. The charges are not there. Therefore, it's a work as a hydrophobic protein. Lysine is here working as a, because of the after modification, it can work as a hydrophobic group. this, if you added succinyl, then what is happening? So replacement of positive charges with negative charges. Then because of negative charges, that solubility can be increased, right? The earlier the lysine, that because remove the positive charge, its solubility decreased. If you added succinyl, then it's a positive charge with negative, therefore it's a solubility increase. And if you added the phosphor group, then you can replace the positive charges with negative. Again, if you added the positive, this one, the lysine, 2 negative charges. Then now the product is final, that protein is come out with the very negative charge, a lot of negative charge, therefore solubility can be increased. If you add in the glyco one, sugar or oligosaccharide, removal of positive charge on lysine, and therefore then our sugars and oligosaccharides are there, then it's definitely we can increase the emulsification properties of the product. If you add the fatty acid bond, removal of positive charge on lysine, as well as again now it's a hydrophobic. Now the fatty acids group is combined with the this lysine, therefore charges are removing, as well as the hydrophobic behavior is improved or the increased. Therefore, accordingly, by by adding the modifying group, you can change the action of these proteins, and we can use those proteins for a different purpose. But very importantly, here we use the lysine, but whatever the neutral compulsion or the neutral benefits, biological benefits or bioavailability of lysine is not losing because of this modification. So that is important. So the other one, it's a chemical modification. Also we can do the enzymatic modification. How we can do it? Protein hydrolysis we can do by using the proteolytic enzymes. Protein broken down by enzymes to smaller peptides and improved solubility and biological value. And the other one is protein cross-linking. Also we can use some enzymes like transglutaminase can covalently link protein together, and also very important to improve the great improvement in gel strength. So in case of that, the sausage production or the sometimes in the fish sausage production or the surimi production, even surimi, you know, that's we prepare some kind of product having very good texture by using we can prepare by the fish proteins, the fish fibers. And in that, to make these fish fibers together, we use the transglutaminase enzyme. That enzyme can link protein together, and finally you will end up with a very nice texture of the protein, like a rubbery nature, or the rubbery nature means once you press it, come out very quickly. And this nature can get by using the transglutaminase enzyme, right? Especially improve the gel strength. Therefore, these now enzymatic modification is really important in the case of protein modification. Increase its here if the protein hydrolysis improved, solubility and biological value also can be increased. The other one, gel strength improved. Therefore, you can use it for a different products development. So how it is happening? Amino acid modification, peptidyl glutaminase converts glutamine to glutamic acid, negatively charged, and can convert an insoluble protein to a soluble protein. So you can see how it's happening, glutamine and glutamate, and then because of glutaminase enzyme, you can change the convert insoluble protein to a soluble protein by changing to the negatively charged. Right, so here the glutamine glutamate is a two different one, and very many proteins can get together by glutaminase enzyme. And first we call the chemical modification. The second one is the enzymatic modification. The third category is we can do the physical modification. How we can do it? Most of the method involve heat to partially denature the protein, like using the alkaline treatment. We can use the partially denature, or we can expose we can unfold the protein by because of the alkaline treatment. But you know about the textured vegetable protein, TVP. We normally eat it as a soy meat. So what is happened to this protein? A combination of heat above 60 degrees, pressure, high pH around 11, that's the alkaline situation, and ionic strength used to solubilize and denature the proteins which rearrange into 3D gel structure with meat-like texture, right? So you may think that yes, we know it's a soy protein. Soy protein is like a powder, but finally what will end up with is denatured the 3D structure of the protein, because you know that once you put it the water, once you add some hot water to the TVP, so you can get the very spongy nature, right? So the spongy nature of the 3D gel structure is producing by the soy protein because we are subjected to the physical modification. Excuse me, one student, please unmute your, so mute your phones, mute your microphones. It's not, it is disturbing to the recording even, to me too. Good water and fat holding capacity can be increased by the physical modification. And also the cheaper than muscle protein often used in meat product, right? So because in the meat products mean different type of meat, let's say sausages, or the different type of hamburgers, burgers, or nugget, or the different type of meat based, muscle based product, we are adding TVP soy protein, because that soy protein TVP, once we get the texturized vegetable proteins we add, because it is having the meat like texture. Actually it's not the fibrous one. The meat proteins are having the fibrous nature, but in the case of textured vegetable protein having it's a gel structure. But when compare these two together, you will feel that both are same. That is why what they do is actually in the market you can see the chicken flavored chicken TVP, or the vegetable TVP, or the beef TVP, or what's the squid, or the dalla, issa, what they do is that the TVP is the same. It's a 3D gel structure. They just cut it in the different type of shape. But there is a very what is that flavor aroma packet, or the spicy packet. So all these the flavors and the aromas and the other, all the things are trapped in that solution. That the lipid based solution is there, it is entrapped there. Then when you are cooking, what you do is you are adding that portion to the TVP. So actually the TVP is having the air pockets. You have seen that the TVP texture vegetable protein is having a air pockets. Therefore that the aromas and flavors are not bind with the gel structure, because gel structure is there, it's a totally now closed structure, but the air pockets are trapped by these flavors and aromas. Therefore once you eat it, you feel that make a isurahi, make a dallo rahi, make a chicken rahi, make a vegetable rahi කියලා එන්නේ එතනින් තමයි ඒක එන්නේ. ඒරුණාම ඒවා අර බයින් කරන්නේ නැහැ. These are the really cooked situation. But in the case of in the meat products, even we can add it. Because it gives the muscle protein texture. That is why we are using textured vegetable protein as an filler. Sometimes we call filler, or the extender, we can say that, because yield we can extend by using the TVP. So therefore we can use this vegetable protein to the muscle protein. So also in the case of protein-based fat substitutes are also there. This simplicity is one trademark, and the milk or egg protein heat denatured and mechanically sheared. On cooling, they form small globular particles that have the small mouthfeel and juiciness of fat. You can feel that milk and egg proteins get mixed together, so you will end up these things. Actually, in the case of you know that the French toast. When you prepare the French toast, you add milk, egg, and sugar together, and you beat it. Then you are adding once you disperse the bread to there, and when you are fried it, so it's giving a very nice taste and a nice and very nice texture, mouthfeel, and the juiciness is there because of this. the simplicity is very sensitive to high heat. Limits is used in processing. So this is the recall about the other one, right?